All right, hello there. So I'm going to do section 15.9 here. I'm doing the whole thing, but of course we started this in class, so go ahead and skip ahead to where we left off, or you can rewatch a part if you need to. So remember that we learned back in regular calculus U substitution, and U substitution was a type of changing of variables, right? So when you did this problem here, what you did is you let U be equal to 2x plus 1, right? And then du was 2 dx, and so 1/2 du was equal to dx. And so if you wanted to change this to be in terms of U, you went like this. You had the integral, this 2 right here can just come out front, and we had to also put a 1/2 to counteract the dx, and so then I can replace du here, and basically I would have the square root of u, or basically u to the 1/2. Now you also learned that if you have these boundaries here, you are allowed, if you like, now you don't really do this that often, but if you like, you can change these to u values. So if x were 0, u would be 2 times 0 plus 1, using our little substitution right here, so that would be 1. If x were 1, then u would be 2 times 1 is 2, 2 plus 1 is 3. So we could make this from 1 to 3, and we could literally just evaluate this and not even remember that there was x's. So this would be the integral from 1 to 3 of u to the 1/2 du, and just keep going with that. We'd get u to the 3/2 divided by 3/2, so times 2/3. Evaluate this from 1 to 3. And so when you do that, when you plug in 3, you get 2/3. You plug in 3, you have 3 to the 3/2, minus plug in a 1, you get 1 right there. And so this is our answer here, and it's the same as if we would have done this and then gone back and like plugged in our x instead and used the 0 and the 1. Either way, we would get the same thing. And so what we were doing is we were changing something, changing a problem. This problem right here was calculating the area under the curve from 0 to 1 of a curve that was the square root of 2x plus 1 times 2, right? And we were going from 0 to 1. Whereas this problem down here was calculating just your basic square root function, square root of x, and it was going from 1 to 3. And so what happens is these areas, they are going, even though my drawings don't look right, but these areas, they match each other in value. They're the same area, but just in a different coordinate system in a way, right? Because this was using like, I should have put a u in there instead. So I'll do the square root of u, I guess. All right, and so that's what you did before. So the definition of what you just did was here, right? And you did a u substitution, you changed the variables, and so this is all the stuff that you learned about this last year. So we've been making changes of variables when we converted between rectangular, cylindrical, and spherical systems. We've already been doing this, right? These changes are the transformations, so we transformed these things, and like when we went from rectangular to cylindrical, you know, we would have a double integral, and we'd had to put our r, dr, d theta, right? Or sometimes if we did a triple integral, we'd have triple integral, and then we'd have dz, dr, d theta, right? And we added that extra r there, or we multiplied by that extra r. Remember when we went to spherical, we did those in 3D, and we put in a rho squared sine phi, and we had d phi, dr, d theta, or you know, that was basically spherical plus cylindrical. But remember, we can also do this double integral, rho squared sine phi, and we could have d rho, d phi, d theta, those types also. So this part that you were doing right here, you didn't really know it at the time. I did allude to it before a little bit, but this little piece right here, is actually has a name. It's called the Jacobian, and the Jacobian is what you put into a problem when you have changed it between types, when you have transformed it into done a change of variables. And so this is kind of like the scale factor by which you have to multiply something by, so that when you're going between these different worlds, it accounts for the changing of the worlds. I'm just making that terminology up there, but that's what it's really doing right there. So this transformation that we're doing, go ahead and fix this on your paper here. This should be U and V right there. So we're basically going to change from our XY world that we're used to our UV world. Right, and so you're going to be given the transformation equations. It would be difficult to come up with those things, and that's another special task, but we're not going to have to come up with those. All right, and so this page is just explaining some pieces about that. But what's happening is we are changing our XY world to a UV world, and we're going to be given equations to do that. Okay, so and then these worlds are kind of interchangeable in a way. So if you have a one-to-one transformation, then that transformation has an inverse transformation. So it allows you to go back and forth between the two. All right, and so here we've come with our first example. Find the image of a set S, where S is a square bounded by these lines right here. So we have our U and V. So U and V, and U equals 0. So U equals 0 would be here. U equals 1. We'll just say that's 1 right there. V equals 0 right there. And V equals 1 right there. So like a square, right? So you have this little area right inside there. All right. And under this transformation, X is equal to V. And then Y is equal to U times 1 plus V squared. All right, so we're going to change these up a little bit. So we're going to number these things. Side 1 is going to be, side number 1 is going to be the equation V equals 0. Okay, so V equals 0. This was, let's see, V equals 0 right here. So this is side 1. Okay, side 2 is going to be U equals 1, so 2. Side 3 right here, and side 4 right there. Okay, all right, so V equals 0. So in our world, if V is equal to 0, I have to turn this into an XY. So I'm going to use this equation right here, right? If V is equal to 0, then that basically transforms into X is equal to 0. All right, and in our problem right here, V stayed, this V equals 0, V stayed when you were at V equals 0 right here. So when V equals 0, you stayed between U equals 0 and U equals 1. All right, so that was like a boundary for us. So V equals 0, this was for when U was between 0 and 1. So if we kind of transform this here, U was between 0 and 1, so then therefore if U is equal to 0, then my Y value would be, using this equation here, would be 0, and then 1 plus V squared, so that would be 0. All right, and then the other one would be if with U is equal to 1, that would be Y equals 1 plus V squared, but remember V is equal to 0, so that would be Y equals 1. So in our case right here, our boundaries are going to be between 0 and 1. So Y is between 0 and 1. And so side number 2. Side number 2 over in our picture right here is U equals 1. And it goes from, stays between V is 0 and 1. All right, so if U equals 1, so let's go ahead and use one of our equations. We'll use this one right here. Then that means we have Y equals 1 plus V squared. All right, so remember though that X is equal to V, so we basically get the equation Y equals 1 plus X squared. Okay, and much in the same way as before, we're going to do this. X is equal to V, so I'm going to use that here and say X is between 0 and 1. All right, so we're going to draw this in a minute. All right, so that's our second, oops, I guess I'll circle this one right here, our second equation. All right, so the next one, side 3. Side 3 was the equation v equals to 1, and that stays between u as 0 and 1. All right, so let's transform that. So v is equal to 1. Well, x is equal to v, so that transforms into x equals 1. And in our case right here, this similar to what we did before, we'll have y equals u, and I have 1 plus, remember x is equal to v, so v is equal to 1. I'm using this equation right here, 1 plus 1, so I get 2u. Okay, so y is equal to 2u, and so if u stays between 0 and 1, that means that u is equal to y over 2, so that means that y over 2 stays between 0 and 1. All right, so that means that would be 0, y, and that's what turned into 2 right here. All right, so we got that equation. All right, so side number 4. Now we don't have to do this that much, but this helps us see what the spaces are, and so it won't be this tedious in the long run, but you'll see it won't be as bad as this looks. All right, so this side number 4 was u equals 0, and in our problem right here, if u is equal to 0, using this equation right here, I could say that basically y would equal 0 also, and u is equaling 0 when let's see, u equals 0 when v was between 0 and 1, so that means that x is between 0 and 1. All right, so it's time for us to draw this. Okay, so this space in our u and v land is equivalent to this space in our x and y land. So our x and our y, and let's see, we've got a bunch of 0s and 1s and 2s, so I think I need to go to 2 on each side, because I think my highest part, right here, is going to 2. All right, so we're going to draw x equals 0. So this side number 1 basically corresponds to x equals 0 between y is 0 and 1. So x equals 0 is right here between 0 and 1. This is 1 and 2. Right, and then our side number 2 is y equals 1 plus x squared. So I'm doing this part right here right now. Y equals 1 plus x squared. So 1 plus x squared, if I plug in 1 or 0, I get 1. If I plug in 1, I get, let's see, I get 2, right? So I get that. This is a parabola, right? Y equals 1 x squared plus 1. So it goes like this. All right, that's side number 2. Side number 3, x equals 1, and it has to last between y is 0 and 2. So x equals 1 is right here, and look how it lasts between x equals 0 and 2. And then the third, or the fourth side, is right there. So basically, if I look at u and v world, that space that we've covered, this little box that we've covered right here, is the same amount as x and y world, this area right there. Now, if you were imagining doing the integral, you might like to do the integral of the box rather than this xy world shape that has the curvy part to it. It's not really that hard either way, but you'll see how some of these, when you transform them, it makes it easier to do the integral. And that's the whole purpose, is to, when you're doing, you transform them so that your integral is easier. Okay. All right. So next you have this thing called your Jacobian. All right. So how is the integral of f of xy over r related to the integral with u and v? So the answer is you have g and h and f have continuous partial derivatives, and the Jacobian is 0 only at isolated points. And so what you do to equate these two things is to change it to your UV world. You multiply in this extra little multiplier, like a little ratio, that's going to help you go between worlds. Okay, and that is called, that transformation piece is called the Jacobian. So let's see how to do it. And it's going to look really awful, and you're going to be like, oh my god, like what is all this? All right, like my funny little cat picture down here. All right, but it's not difficult, okay, once you notice the pattern. So to do the Jacobian, you do the determinant of some derivatives, okay? So remember what this derivative means, like right here. You do the derivative of x with respect to u. Then you do the derivative of x with respect to v. Then you do the derivative of y with respect to u, derivative of y with respect to v. So you just do some partial derivatives right there, and then you do the determinant. So remember, you crisscross and subtract, right? That's all this is saying right there. Okay, so for polar coordinates, let's look at some of these things. Remember, for polar coordinates, x is equal to r cosine theta and y is equal to r sine theta. So let's do that. What's the derivative of x with respect to r? So derivative with respect to r, the derivative of r would be 1, and the cosine just hangs out. So that's how we got cosine. Now what's the derivative of x with respect to theta? So this time r hangs out and stays there. Derivative of cosine is negative sine. So there it is. All right, now I do the y. On the bottom, dy dr. So the r, derivative of that is 1, and the sine just hangs out. So there it is. And then the derivative of y with respect to theta, well, the r just hangs out, and the derivative of sine would be cosine. So look, cosine theta times r cosine theta turns into r cosine squared. Minus a minus turns into plus r sine squared. And you can, remember, factor out an r, you get cosine squared plus sine squared. And so that's why you get, and that's equal to 1, so that's why you get r. So really all along, r, when you're putting that into your, with your polar coordinates and your cylindrical stuff, you were putting in the Jacobian, you just didn't know that that's what it was called. Okay? All right, so you just have to put that every single time. And the explanation for spherical is in the book right there, but I figured you would just believe me. You know, how you have to put the rho squared sine phi. All right, we don't want to see all that. All right, so we're going to practice finding the Jacobian of these transformations right here, of this one transformation. So we're not going to go ahead and define these things or anything like that, but look at how we have like our r and our theta, and we have our xy world, and this is kind of like my uv or r and theta world, my u up here. So imagine which one is easier to do the integral. It would be easier to do the integral of this one, so that we're basically transforming this to that. Okay, so let's find our Jacobian. So our Jacobian is going to be the determinant. So I have to go across the top using my x. I do dx du. So dx du, the derivative of the u part would be 2u. And then for the next piece across, I do dx dv. So the derivative of the v would be negative 2v. Now in the bottom row, I do the y. So the derivative of y with respect to u would be 2u, and the derivative of y with respect to v would be 2v. Then I just do my crisscross determinant, right? So I get 4uv minus, and it's going to be a minus again, so plus, and it's going to be 4uv, so 8uv. So when I go ahead and do this integral, if I was going to find the area of this space right here, this double integral, then I would multiply in there an 8uv. Okay, so every once in a while you have to do a triple integral. So don't worry, we're not going to do many of those, but you basically just do all the variables. So you do x with respect to u, v, and then you notice a w, then you do y with u, v, and w, then z with u, v, and w, and so forth. So we're going to do that one here. So our Jacobian would be the derivative of x with respect to u is v, the derivative of x with respect to v is u, and the derivative of x with respect to w is 0 because there is no w. All right, now here the derivative of y with respect to u is 0, the derivative of y with respect to v is w, and then finally the last one is v. Then I got my z that I'm using. The derivative of z with respect to u is w. The derivative of z with respect to v is nothing. The derivative of z with respect to w is u. All right, now remember how to do the determinant of a 3 by 3. Remember when we would do I, J, K, we'd have our two vectors here, and we'd basically kind of cross these off and do the determinant right here and multiply that by I. So that's a way to do the determinant of a 3 by 3 matrix. So here we go. So I'm going to take and multiply V by the outcome of, when I cross these out, what's the determinant right here? So that would get me WU minus 0. So it gets me WU. And remember in the middle part, we would add, but we're going to change the sign. So I get U, which is my center. So then I cross this and this off, and I have to crisscross U times 0 times U, so that's 0 minus VW. All right, and then plus the last part, well this time there's a 0 here, so I'm multiplying 0, and when I cross these off, I get 0 minus W squared. So I'm going to say that it's minus W squared here, but it doesn't matter because it's times 0. All right, so we basically have right here VWU minus, that turns into a plus VWU, so I get 2 VWU. So that would be the Jacobian there. Okay. All right, so let's see how we're going to do all these. So we're going to do a change of variable with double integrals right here. And so I want you to notice what we're doing here. So your first job, this is going to be the steps you do. I see I have them numbered here. All right. So this is someone trying to do this integral right here. So somebody is trying to calculate this integral, and it's kind of yucky because if we look at the picture, so we're trying to do this integral, and we have these boundaries that are pretty gross. Look at this shape right here. You know, these corners don't even line up, so we can't even split this in half. We'd have to like come up here like this. We'd have to do like this section, then we'd have to like probably split this one here and do this middle section, and then finally the last section if we wanted to do this integral very nicely. All right, and so it'd be a horrible pain, and so it wouldn't be fun. All right, and so what you can do is make it a nicer problem to do. So we're going to sketch the region that we have. That's going to be our first job, like sketch what's being given to us, right? And like note the boundaries and the XY plane and all that. So that's already done for us here. All right, step 2. We're going to have to solve the equations they give us for U and V, because they're going to give us the transformation equations, and we're going to solve, if they give it to us in U and V, we're going to solve them for X and Y. If they give X and Y, solve them for U and V, vice versa. Okay, so let's do that. So in this problem right here, let's see. I don't know. Let's see, y, oopsie. I would get y equal to 2v. So that one seems to be done. So over here, I would get 2u equals 2x minus y. Well, I want everything in terms of, I want to solve for x, and everything's in terms of u and v. So I'm going to put this y on the other side, but I'm going to change it to 2v because that's what the other problem says. So 2u plus 2v equals 2x. So that gets me x equals u plus v. All right. So there's my equations solved for x and y. All right. So then we're going to find our boundary equation. So this is like the most tedious part right here. Okay, so we had our 4 boundary equations right here. I had these 2, and then y equals 0 and y equals 4. Remember, those were the boundaries of this shape right there. That was right there in our picture. Okay, we have to transform them to be u and v. All right, so this is going to be the worst part, but let's use our equations over here. So x was equal to u plus v, and y was equal to 2v. So if somebody tells me that, I'm just going to take those things and substitute them in there. X was equal to u plus v, and y was 2v, so 2v over 2. So let's see if we can solve that out. The 2's cancel, the v's would cancel, so I'd get u equals 0. And so you see that equation right here. All right, and then over here, x equals, so again, I'm going to have u plus v equals 2v over 2 plus 1. So again, the v's cancels, and I get u equals 1. So there. Y equals 0, so that would just be 2v equals 0, so v would equal 0. Okay. And y equals 4, so 2v equals 4, so v would equal 2, right there. So that weird like slanted shape has now turned into this. And so when I go and do my double integral, all I have to do is, if I have like du and dv out here, all I have to do is go from, u goes from 0 to 1 and v goes from 0 to 2. I don't have this nasty integral anymore. We'll go ahead and change our problem right here. We'll put our Jacobian in there and it'll be easier. Okay. All right, so find the Jacobian. So I have to do the derivative of x with respect to u and the derivative of x with respect to v. So that's what this is saying right here. So the derivative of x with respect to u would be 1 and v, same thing. Then I have to do the derivative of y with respect to u, so that would be 0. The derivative of y with respect to v would be 2. So my determinant would be 2 minus nothing, so 2. All right, so there's my Jacobian, nice and easy. So this piece right here, remember we have our two equations. I have that x equals u plus v and y equals 2v. And so this equation that I have right there, let me make sure of that, x equals u plus v, yeah. So I would have, if I'm trying to change this, I'd have 2u plus v minus y is 2v all over 2. So what happens there is my v's cancel out, 2v and 2v cancel out. I just have 2u over 2, so I just have u. So that's why you see this little u appear right there. Then we have our Jacobian, which we found earlier, is there. And so really I'm just doing the integral of 2u, which is 2u squared over 2, which is u squared. I'm evaluating that from 0 to 1, so that comes out to 1. So then I'm doing the integral of from 0 to 2 of 1 dv. Well, that is just v from 0 to 2, which is 2. And so the integral becomes much easier to do because we prepped it by fixing the world that we were in. Okay. All right, so we're going to do that in this one problem here. We're going to do all the steps, and then I have for you on the example 5 and 6, I'm going to I'll talk about them in class a little bit, but I'm not gonna like do the video of them. I'm just gonna give you like the solutions and kind of go through them, and then there'll be all the writing and stuff will be there as well for you to look at. Okay. All right, so in these examples, yeah, we use the transformations given. So they're giving me the transformation equations, and they are already solved for x and y. So I want to solve them for u and v. So this will be the most tedious part. But first, let's do our steps in order. Let's draw what we have going on right here. Okay, so I have a square with these vertices. So step 1, let's see what's going on. I have, let's see, they go up to 5. So 1, 2, 3, 4, 5 on the x, and it goes to, let's see, 3. And then -2. All right, so here we go. So 0, 0. Okay, well, I'll put A, B, C, and D. So point A, 0, 0. Then 2, 3. And then 5, 1. And 3, -2. So 3, -2. All right, so you can see that it is a square, okay? And so this is the space that we're trying to do, but also notice that it's like offset, right? Letter B is at 2, 3, and letter D is at 3, -2. So it's not like B and D line up with each other vertically. And so the space would be really hard to like do the integral of because I can't like split it nicely. It'd be really gross. So instead, we're going to transform it. So step 2, we're going to take what they gave us here and solve. If it's solved for x and y, let's solve it for u and v. All right, so let's take a look. So just have to start in some way. So I'm going to take this guy right here and solve it for u. So I'd get x minus 3v equals 2u. So u would equal x minus 3v over 2. Okay, and then why don't I see what's going on here? Let's solve this one over here for, let's try to put that in the other problem. So u goes in right here. So I get y equals 3. U is really x minus 3v over 2 minus 2v. So let's see what that does for us there. I'm going to multiply everything by 2 to make it the fraction go away. So I got 2y equals 3 times x minus 3v minus multiply by 2, so I get 4v. All right, so 2y equals 3x minus 9v minus 4v. All right, so 2y equals 3x minus 13v. And let's see, I'm trying to solve for, I can solve for v. So if I solve this for v, I'll make this 13v equals 3x minus 2y. So v would be 3x minus 2y over 13. So good. So I got an equation in x and y for v. And now I'm going to put that back in this problem over here. So this is the worst part, but it won't be too bad after this. So u equals, let's see, I now have an equation for v, so I'm going to do x minus 3 times v. So that's 3x minus 2y over 13. It's all over 2. I'm going to put that 2 over here. All right, so let's multiply everything by 13 to make this a little easier. So I get 26u equals 13x minus 3 times 3x minus 2y. I already have an equation for v, so yeah, I'm going to solve this one for u. So let's see. 13x is going to be minus 9x, so that's going to be 4x, and it'll be plus 6y. I have 26u here, so u equals 4x plus 6y over 26. Or, if I divide everything by 2, it looks like I get 2x plus 3y over 13. And so I know that seems horrible, but that part has to be done. And it won't be too hard. This one might be a little bit harder than like what you have to do. All right, so next we're going to find, we're going to transform everything, right? And so basically what I have going on right here, if I have these points given to me instead of equations, what I can do is transform those points. So step 3, I had the point 0, 0. So remember, this was my x, y. I want to transform this to u and v and see what it looks like. So if x and y were both 0, u would be 0, could be 0 over 13, and v would also be 0 because it'd be 0 over 13. All right, next point that was given to me was 2, 3. So if x and y were 2 and 3 in this problem, so I'd get 4 plus 9, so it'd be 13 over 13, that would be 1. And for v, I would get 3 minus, I'm sorry, put a 2 in, so I get 3 times 2, so 6, 6 minus 6, so I get 0. Okay, so keep doing that. If I put in 5, 1 into both of these equations here and here, I would end up getting 1, 1. And if I put in 3, negative 2 into these equations again, I would get 0, 1. So look at what we have. In my u and my v world, I just have this square. I have 0, 0 to 1, 0 to 1, 1 to 0, 1. I just have this area there. So this area, that red area, is the same as this blue area. Okay? All right. So let me add a page here. And get a blank page. So now we are going to do step 4, our Jacobian. So my Jacobian, I have to do the derivatives with respect to x and y. So I have to do the derivative of u with respect, the derivative of x with respect to u. where were we? Sorry about that. So the derivative of x with respect to u, so remember here's our equations right here, is 2. The derivative of x with respect to v is 3. And then it'll be 3 and negative 2 for the next part. So I'm going to get this matrix here. I get 2, 3, 3, negative 2. So when I crisscross, I get negative 4 minus 9, so I get negative 13. Okay. And remember, we didn't notice it before, but part of the formula for the Jacobian is that we do the absolute value of the Jacobian. So the Jacobian is that determinant, but I have to do the absolute value of it. All right, so if it's negative, I have to make it positive. All right, so now we're step 5, we're going to do our integral. Set up my integral. Remember, I had a unit square, so 0 to 1, 0 to 1. I put my 13 in there. I just put it outside here. Now, our original problem had this. It had x plus y. So if I want to do that, I have to add these two things together to get it in u and v form. So if I add those together, I get 5u plus v. All right, so that's what I'm doing the integral of, 5u plus v. And I have du dv. And then all I have to do is do that integral. So the integral with respect to u would be 5u squared over 2 plus uv. Evaluate this from 0 to 1. So luckily 0 would go away. So if I put in a 1, I get 5 halves plus 1v. All right, so now I'm going to integrate this with respect to v. So I get 13. Let's see, I get 5 halves v plus v squared over 2. I have to evaluate this from 0 to 1. So luckily the 0 goes away. So if I put in a 1, I get 5 halves plus 1 half. So you see how the integral becomes very easy to do, and I get 13 times 3, which is 39. Okay, all right, so these last two examples, example 5, this is going to turn into something that you can, it would be preferable to use polar format for, and you'll see that in the notes there. And also then example 6 is just like an example of having a 3D. You notice there's 3 integrals here. It's a 3D space that we're doing the integral over. And so that's just an example of that. And you'll see those in the notes. You do not have to copy them down. I just wanted you to see the one example there, and you will be responsible for knowing how to do that. All right, bye-bye. And remember tonight, I think 1, 7, and 9, I think is what you're gonna do after you finish the video. Do 1, 7, and 9, and then we'll do 11 and 13 in class.